Let's talk about open sets. To do this, we'll first define what an epsilon neighborhood is, because this helps us to build our definition of what an open set is. And then we'll go through some silly examples to show that a set is obviously open according to our definition, and to show that a set is not open because it contradicts our definition of an open set. Let's do it. So here's our definition of an epsilon neighborhood. It says, given A within the real numbers and an epsilon greater than 0, the epsilon neighborhood of a point A is going to be defined by this set. So the set of all x's within the real numbers such that the absolute value of x minus a is going to be less than epsilon. So basically, if we were to visualize this on a number line, if we have a point A, our epsilon neighborhood is going to be the open interval that's centered at A with a radius of epsilon, right? So it's going to be all the way from A minus epsilon to A plus epsilon. So you could write this in this set form, or you could also write this as an open interval, right? The open interval from A minus epsilon all the way to A plus epsilon. So this is the definition of our epsilon neighborhood. We now use that definition of an epsilon neighborhood to build our definition of an open set. So a set omega, contained entirely within the real numbers, is defined as open if for all points within our set, there exists an epsilon neighborhood, as defined above, such that that epsilon neighborhood is entirely contained within our set. This is our definition. Let's now use that definition to show that the open interval from A to B is open. This is obviously true, but we want to show that it satisfies our definition. So if we come over here and think about what we're doing, if we want to satisfy our definition of an open set, we want to show that for every single point within our set, there exists an epsilon such that when I create my little epsilon neighborhood around that point, this epsilon neighborhood is entirely contained within our original set. If we can do this for every single point, then we will have shown that it's open. So we really need to carefully choose epsilon for this scenario, and this is how I'm going to propose we do that. Let's say that for this point right here, we were trying to choose an epsilon. Well, you can see that the distance x minus a is obviously less than the distance b minus x. So let's pick that quantity, x minus a, to be our epsilon. Then we will have created an epsilon neighborhood that's obviously entirely contained within our original set. So let's do this for every single point. So basically the recipe is, look at the distance b minus x, and then look at the distance x minus a. Whichever distance is smaller, choose that value to be your epsilon. So this is me just writing that out. So we pick any arbitrary x within our interval, right? And then we pick our epsilon like we were talking about earlier. Look at the distance b minus x, look at the distance x minus a, pick the minimum between those two. And this will be greater than 0, as is required by our definition of an epsilon neighborhood, because we're picking an x between a and b. So a is going to be less than our chosen x, which is going to be less than b. There you go. So if we pick epsilon like this, then for every single x within our interval, we're going to have that the epsilon neighborhood around it is going to be entirely contained within our set from A to B, and so the set from A to B is an open set. Now let's use our definition of openness to show that the set just containing the point A is not open. We'll do this by contradiction. So for your contradiction proofs, you suppose that the opposite is true. So we're going to suppose that the set just containing the point A is actually open. If this is the case, then we have our definition of openness, right? There exists an epsilon greater than 0, such that for the epsilon neighborhood around A is the only point in our set, this is entirely contained within our original set just containing the point A. This is just another way of writing that with open intervals. The place that we're going to draw a contradiction is showing that there's an element in our epsilon neighborhood around A that is not contained within our set just containing the point A, right? If there's something in here that's not in our original set, that's going to violate our definition of openness, which we said was true. So the point we're going to pick to demonstrate this is A plus epsilon over 2. So if we come up here and try and visualize this, if we have an epsilon neighborhood around A, that's going to look like this, right? This is already a little bit silly to draw because you can see that for any epsilon, the epsilon neighborhood is not going to be contained within A, but this is how you do that rigorously, right? So our point A plus epsilon over 2 is going to be right here. This point is clearly contained within our epsilon neighborhood for any value of epsilon, but it is obviously not within the set just containing the point A, hence a contradiction. Here I've just written that out. Obviously, A is going to be strictly less than A plus epsilon over 2 because epsilon is greater than 0. And so A plus epsilon over 2 is not going to be contained within our original set. And so our set is not open. That's all she wrote. I hope this was a good introduction to open sets, defining them, showing a set is open, showing a set is not open by contradiction. If this video is helpful, consider pressing the buttons, the likes, the comments, the shares. It really helps me out. And thanks for watching. I appreciate all of you. I post on TikTok and Instagram as well, so show the love if you're feeling it. Later.